In this video we're going to take a look at the Leet Test challenge on Hack the Box. It's an easy pwn challenge and the description says, are you Leet enough? So let's download the files to begin with, or the file. We'll take a copy of it into our local directory and just begin by doing our usual basic file checks. So we'll start by checking the file type, and we'll see that it's a 64-bit LSB executable, it's dynamically linked, and it's not stripped, so symbols and things like that aren't going to be removed. It'll make it a little bit easier to reverse engineer. We can run strings-n10 to get all strings 10 characters or more and get an idea what's going on in the program. So it looks like it's going to try and take a name from us, it's going to print something back to us, and we're either going to be allowed in or we're going to be told, sorry, you're not Leet enough, come back later. We can see some of the imports and functions listed here, so that's cool. Let's do checksec and see what securities are in place. NX is enabled, so if we are able to overflow the buffer and inject some of our own shellcode, we're not actually going to be able to execute it on the stack. There's no canaries, no pi, so we don't need to worry about that. We don't need to worry about the pi base and break RVA and some things that we've used in some of the past pwn videos. Okay, cool. So before we open it up in Ghidra, let's just try and run it. We'll chmod +x Leet test, and it asks us for a name. Put in a name, crypto. Says we're not Leet enough, come back later. Let's try and put in a bigger name. Alright, it doesn't seem to be crashing. Let's put in an even bigger name. And we don't get a segmentation fault. In fact, the input that's cut off just loops back into the next input, so it doesn't actually look like there's a buffer overflow vulnerability here. So we could have a look with ltrace and try and work out what's going on here. We can see it's opening dev view random and it's reading in some random bytes, 4 bytes, and then it checks the name. It's asking for a name. If we say crypto, can we see what it's comparing it to? And we can see it's reading in 256 bytes, but it's not actually, it's using fgets, but it's not actually showing us what it's comparing it to there. It's not comparing crypto to some predefined username that it's going to accept. So, and then eventually we get a sig alarm, an alarm clock that's going to close it down, which you could patch out with a binary, but maybe we won't need to. Let's open up Ghidra and decompile the code. So create a new project, just call it Leet test, and then we can import a file, import Leet test, and just do all the default OKs and yes and whatever it asks us. Okay, and then we can double click on the file, do the same again, just go through all the defaults. And now we have access to our code. So because it's not stripped, we're able to go in and we're able to see the functions. No problem here. We can go in and find the main function. If we just search for it, we can see here main, and that'll take us straight to the code. Again, if we weren't able to do that, we could have looked for the entry and then have a look to see what functions are called, or we could look for strings and then go and look for something like this dev urandom or welcome to Hack the Box, and then we know, okay, that's where we want to look, so we can see that it's referenced at this point in main, and then we can easily jump to the code. So let's have a look what's going on in the main method. So if we start from the top here, we have the variables declared, we have this buffer which is defined of 280 chars, and then as we get into the code, there's this local 138 variable where the dev urandom's opened, and then it reads 4 bytes into the local 13c variable and then closes the dev urandom file. It then performs this AND operation, which I believe is masking is a masking operation, so that only the last half of, I guess, 32 bits or 4 bytes are taken. I'm not 100% sure, I believe so, but I don't think it's too important to us right now. Let's move on. We have this while loop, which is what we observed happening, where it keeps asking us for our name and it reads a name in from us. Here we can see that it takes in 100 hex, which we can go and highlight this here. We can calculate this manually. It's quite a small one to do. So to calculate the decimal equivalent of this, this is basically base 16. So this 0 would be, if this was a 5, that would be 5, for example. That can go up to 16. This second 0 is whatever value is here times 16 to the power of 1. That's a better way of describing it. So whatever we have in this last 0 is, in this case, 0 times 16 to the power of 0. The second value is 0 times 16 to the power of 1. And then this value, which is a 1, is 1 times 16 to the power of 2. So it's basically 16 squared, which is 256. So we can just go and highlight this on the left hand side though, and see that it changes to, you can see the decimal is 256. So it reads in 256. The buffer is 280, so there is no buffer overflow there. That's what we observed whenever we tried to put in a really long input as well. So there's some other vulnerability that we need to exploit. And what happens after this? It takes in the string with fgets. It prints that back to us right here, local 128, and then it's going to compare local 13c. It's going to multiply local 13c by LeetCode, which again we can go and have a look at the decimal value here. 32 million, is it? 32 million something. And it's going to compare that value with whatever's in this winner variable, which is in the data section, .data right here. We can see the address of it, and this contains Cafe Babe in hex, which again we can highlight it. We can see, oh, it's not showing me. Maybe we can't easily do that there. Okay, well, we could go and convert this anyway somewhere else. We put this into ASCII2hex.com or CyberChef, or go and convert this in Python or something like that. But essentially then, we don't control, this is just a number which we're not going to be able to control, this LeetCode. However, local 13c is the value which is read in from dev-urandom, and if we go back to actually dev-urandom there, or well, yeah, that's read into dev-urandom, and then we have the winner value which is in the .data section. So we have a couple of possibilities. We could potentially try to overwrite local 13c, this dev-urandom value, with the value of winner, Cafe Babe, divided by LeetCode, and that way if we're able to assign that into local 13c, we're going to get to this point of the code, it's going to multiply that by LeetCode, and it's going to get back to this value of winner. So if we were looking to see what we needed to make the urandom value equal, let's go and we'll do Python-C, and then we can try to just print out 0x Cafe Babe, which is the value in winner, divided by 0x LeetCode, which should then equal 13c, and here we get back 10.5 and a long decimal number. So that's a potential issue which we'll explore later. In fact, no, let's explore it now. Let's go to ASCII2hex and see what happens when we try to represent this decimal value. You'll see there we've got two separate values showing. If we were to go to, let me find a tool to convert float to hex. I'm going to try and find a tool like this online, and if we put in our float value, convert that to hex, you'll see that's rounded that down. Similarly, if we convert that back now, we're not going to get the same value. And essentially this could be an issue for us. So what else could we do? Well, we know that we may also be able to, or another target for us to overwrite, since we're not able to overwrite LeetCode, we could try to overwrite this winner with another value. So it's currently Cafe Babe. What if we were able to overwrite, if we were only able to overwrite 13c with the integer, we weren't able to overwrite it with that long float, maybe we could overwrite this with 0, and then 0 times LeetCode equals 0, so then we would also need to overwrite the value pointed to by winner with a 0 as well. So this is a potential route for exploitation. We know that if we're able to meet this condition, that's what's going to print the flag for us. There's no use us trying to inject shellcode and things like that because there's no buffer overflow vulnerability, and even if there were, no execute is enabled. We can't execute code on the stack, so we want to so let's look into the vulnerability that we might be able to exploit here. So we know that we only have one place where we can input data. It's not vulnerable to the buffer overflow, but our input is printed back to us with this printf statement, and it doesn't specify what format that should be in. So with these printf statements, if you just provide a string here, if you just provide some text, it's just going to print that out. But it's possible to provide a format specifier like %s for a string, and then have whatever input is provided as the variable be formatted in that way. But there are plenty of other format specifiers, not just strings, and since the developer hasn't specified what format this should be in, they've left that up to an attacker to potentially inject that. So let's go and have a look and have a look at these printf or format string vulnerabilities. It's not my area of expertise, and this challenge took me quite a long time to solve, so maybe that'll come across when I'm trying to explain some of this stuff, either now or later, we'll see. So let's just first of all look for format string specifiers in C. We'll go to the first link here, and this tells us different ways that we can different format specifiers that we can use. So if we want to represent some data as a signed integer, we can use this %d. If we want to represent it as a character, we can use %c, and etc. We've got plenty that we can use here. Some particularly interesting ones are going to be the string, the pointer, so we can actually print the memory location that's pointed to. We can also print in a hexadecimal representation, and then this %n is a particularly interesting one, which actually allows us to write data to memory. So here are some examples of the format specifiers being used. If we wanted to test this, in fact, before we go to test it, let me open up an article which I found particularly helpful in explaining this vulnerability and finding out things to try. So let's have a quick look at this. So I'll leave a link to this article in the description, along with a lot of other articles which will be more useful probably than this video in helping to actually understand the vulnerability and how to exploit it. But let's just flick through this article and see what we can take out of it for now. So we have some different format specifiers which are listed here. They've mentioned the decimal, unsigned decimal, and the one for print in hex. They also mention here that the string format specifier, which we saw right here, all of these specifiers are going to interpret something off of the stack for us. So each one's going to interpret a value either as a pointer or as a decimal or as a character or whatever specifier we give it. But the string specifier is not actually going to it's not going to format that value off the stack as a string. It's going to format the data that is being pointed to by that value on the stack as a string. Hopefully that makes sense. I'll try and explain it with an example a little bit later as well, but that's basically what's being mentioned here, is that the %s indicates that the data should be a pointer to a string. So it's not going to interpret as a string, it's going to be a pointer to a string. Alright, so how can we exploit this anyway? In this case, they actually have some format specifiers in the string. In our case, we don't have any at all. So let's go and try and specify some, and we'll see, for example, in this case here, printf, all they're given is 20 %x's in order to print 20 items off the stack. So let's go and play around with that now. So let's try and run this again, and this time let's pass in, let's say %d as a specifier. We can pass in as many as we want to here, and you can see that this is returned. In our case then we put in 7 %ds, so it's come back with 7 values, 7 decimal values, and some of them are zeros, some of them are big negative integers. We could go and say, let's print back, let's do %s. You see that's come back with null. Let's try that again. And we got a segmentation fault. So this was the issue that we'd seen here with the %s actually not trying to represent. In this case, we have our integer values, but rather than trying to interpret those as a string, it's actually tried to go to this address in memory and then interpret that value as a string. And in the case that the addresses aren't valid, then it's going to present a segmentation fault. So in order to get around that, let's just try this again. Let's experiment with a couple more format specifiers. There we were able to do the character method. As you can see, we could try and let's do some pointers. So here we can actually see some stack addresses because we're printing the pointers, and we can print the hexadecimal representation. So there's printed in hex, and you can see that these values are being printed out. So if we wanted to get something as a string and not get the value which is pointed to by that location, not get the data that's pointed to as a string, we can simply print it as hex and then go and convert that somewhere, either on ASCII to hex.com, or you could just automate this with Python to convert that to a string. And that's a way of getting around fuzzing for strings without having to worry about segmentation faults as well. So what we're going to do now is try and put together a simple fuzzing script just to loop through and try and print out values in different formats and see if we can find anything of interest. So let me clear this. Let's copy our pwnTools template over. I'm going to call it fuzz.py, and let's open that up in Codium. And we need to plug in some values here. We don't want to need this find instruction pointer function at all because there's no buffer overflow. So let's just get this out of the way. Let's set up our executable. So it's called leet test, and we can set our context level to debug if we want to get some more information. In this case, I'm going to leave it at info for now. We'll change it if we need to, and let's just take all of this stuff out for now, and we can start the fuzzing process. So one other thing I want to mention, let's go back to this article, and if we wanted to print out those items on the stack, we can print 20 items off the stack. In fact, let's grab a copy of this. Let me go back and quickly run that again. There's our 20 elements. We don't have the zeros between, we don't have a space between them, so it makes it a little bit harder to read. But another way that we could, if we wanted to access the 20th element, another way we can do that is by using this. We can say percentage, let's say 20, because we were doing 20 there, percentage $20 $X, and that's going to print the 20th element as a hex value. So let's try that. If we run this again, and we do percentage $20 $X, and you'll see here it's printed out 340, which was this value here, so it's only printed out the 20th element. So this can be quite important, not just because we don't want to have to type out all these X's and we maybe don't want to print out all of these values, but also because in some cases our buffer isn't going to be long enough to print out all of these. So whatever you're trying to access could be a long way, could be quite far on a stack, and you might need to print a lot of X's, and if the buffer isn't big enough, that's no good. But if we're able to just say, well, we want you to print the 200th element of the stack, there we go, and it will be able to print that out without us having to do these 200 percentage X's. So that's how we're going to put together the fuzzing script as well. And right here I'm going to say, let's say for I in range 100. We'll fuzz for 100 for now. And we can say, let's try io dot send line, and we're going to send it in this percent. We'll put in here percentage curly braces dollar, and then whatever format we want to give it. In this case, let's say X to print it as a hexadecimal value, and then we can just say dot format I, and in each instance of the loop it's going to insert the ith value in here, and then it's going to print out that element. So we send that off, and then we want to receive until, if we go back to our code here, we want to receive until we get another hello. So let's do that again. We want to receive until we get the hello, and then whatever comes after that is the value that we want to print out, because that's going to be the value on the stack that we're accessing. So we'll say io.receive until, we want to receive it until hello, and then the response is what we want to print out. So then we can say that's our result. We want to capture the result and just say receive line, and then we can print that out. And we want to know which element it is as well, so let's say it's the ith element. And then just give it the result. If we get to the end of the file, we can say accept end of file error and pass. If we were trying to print out the, oh, I've missed a colon. If we were trying to print out each element as a string, let's actually try this again. Let's try it first of all with the hex. We'll run that first. Let me clear this, and we'll run Python fuzz, and we'll see that we get our 100 elements. It's given us an index each time, and then it's printed the value as hex. We could do that again. Let's try that again for, change that to print a pointer. We can run through that, and now we're seeing what look like to be some stack addresses. So if we're able to identify what the stack addresses are and find the offset from these to other locations on the stack, we can potentially combine this with other kinds of attacks. So we can, as we've done in previous examples, if we can, for example, find our entry point to libc and then use the offset to calculate our how to access other functions from within libc, then we can build up some pretty devastating attacks. But what's going to happen if we try now to print this as a string? Let me run that. And you'll see we only get 4 back. So the issue is that it still crashes. So if we wanted to actually, let's see if we can try that. Okay, that's not a good way to do it. Let's go back and send. Actually, instead of doing the IO start there, I'm gonna say IO equals process with the exe, and then we'll just do io.close. Let's try that. Okay, it's not helping that we have this. Let me change this to error only. Okay, so essentially we're just launching the process each time. So even if we get a segmentation fault, it doesn't matter, because each time we're going to be launching the process again, and that's a way that would allow us to go through and go through as many elements as we want to and print as strings. So in some CTFs it might just be a case of somewhere one of these values is actually the flag and we're able to print it. You can see it's actually got down here, it started to get into the environment variables on my system. But yeah, I thought we'd just demonstrate that as well. Let's also see what happens then if we go back to our fuzzing script, and I'm going to take that out, the strings stuff. Let's just do this. Actually, what I'll do is we'll keep that in there just in case we want to go back to it. but let's just set this to start, because the program doesn't crash. Ordinarily it just loops through. If we go, each time we give an incorrect name, it just loops through. We can just leave the process running. So we have that running, but let's also see if we can place something on the stack. So if we, before we send our format specifier, let's try and just send out some A's. Actually, let me try and make them multiples of 4. 1, 2, 3, 4. Oh, that's 5. Alright, let's send 8 A's for now, see what we get. We're still printing as strings, are we? Yes, okay, so we'll print it as hex just to make sure we're actually able to print all the values. And okay, I'm not seeing, we see the A's here, but what we'd expect to see as we're printing in hex is start to see some 4 1s, which I'm not seeing. So let's go and do this again. 1, 2, 3, 4. We'll run that again. And now we start to see our A's. So we need to write, is that, I think that was 12. We need to write 12 A's. So we needed to write 8 bytes before those last 4 bytes would actually show up on the stack. But what does this mean? Essentially, this means we can chain this technique to print any address. So we know that the string format specifier is going to print the data pointed to as a string. So if there's anything in memory that we want to print as a string, all we have to do is be able to inject the address of that onto the stack and then ask to interpret that as a string. So now if we try to interpret this 12th element as a string, this 12th element on the stack, it's going to go to the address 41414141, and it's going to try and interpret whatever's there as a string. Obviously it's going to have problems because that's not going to be valid, but you can get an idea anyway how that can be used. So in the example that's given here in this article, they print out dead beef. You can see here they print out dead beef, and then they use the percentage %x to traverse the stack to get to the location of this dead beef, and that's going to be then interpreted as a string. So it's going to then try and go to this memory. It's going to go to this memory address and then interpret the data pointed to it as a string, meaning that essentially you can access any memory location of your choice as long as you're able to inject this onto the stack. So when this technique is combined with the ability to write to memory, it obviously increases its potential. Let's have a look at what's been described here for the memory write. So the %n format specifier is a special case format specifier. Instead of being replaced by a function argument, %n will cause the number of characters written so far to be stored into the corresponding function argument. So here's an example of a printf, and there are 5 1s in the string, and then a %n, and then we have the numchar, and in this case it's going to store, it will store the integer 5 into the variable numchar. So it says here that using dummy output characters and width control in format specifiers, the attacker can now write arbitrary integers to the location pointed to by a function argument. The following is an example of a width control in format specifier, which helps attackers avoid extremely long exploit strings. So this is kind of like what we talked about there, where we can provide 10 in this case. So we can provide 10 to say the 10th element rather than doing 10 %d values, and that'll prevent us from overflowing the buffer or from causing a program to crash. And then they also note that by using length modifiers, attackers are able to control the amount of data written with fine-grained control. For example, %n will write 4 bytes to the target address, whereas %hn will only write 2 bytes. So we can go back again and look at these specifiers, and we can see that we have different data types here. So let's actually, if we go back to our code, and we can look at our fuzzing script, And if we go back here and actually say LLX, you can see that we get longer values. So if we look at the values here, we had 340, and these are the values that we get now. We can go back and modify these again if we were to change that. Does that change decimal? What was the example they gave? H, I think we'll do. So you can see there that it's only taken in 2 bytes in those examples. So this is in terms of reading, but if we wanted to write, that's something worth bearing in mind as well, that the length can give more fine-grained control. So I think we've looked at everything we need to from this article for now. Let's go and try and put this together. And I'm going to put this together first of all in PwnTools using some functions which are built-in available to actually deal with format string vulnerabilities. The main reason that I did this is because I was having a lot of problems doing this manually, and I figured the best way to learn how to do it was to use the automated function and then go through and debug it in GDB and see exactly what was happening behind the scenes and what was actually sent by PwnTools. So let's start doing that now. So I'll comment this out for now. We might want to check it out again later just for printing out some of the values, but for now let's have a look at this format string specifier. So I'm going to search PwnTools format string, and we can go and have a look at the documentation. So provide some tools to exploit the format string bug. Here's an example that it gives, and you can see here that it creates, in this example they've created a function called execFormat, and it's going to execute, it's going to launch the program, it's going to send a line, it's going to retrieve the data, and that's the function which they pass in as an argument here to the format string creation. Here's an automated example, so this is probably what we'll be looking to do. So it creates a format string object and it passes in as the execute format this send payload function, and this is going to be sending the, it looks like this is going to do the fuzzing for us essentially, and then they just call format string.write, and essentially this %n that's being used in those cases, rather than manually identifying it, in this case it takes in the address that you want to write to and then the value that you want to write, and it's going to do that for us whenever we call execute writes. And then we can go in and we can actually see what it's doing behind the scenes and use that hopefully to gain a better understanding. So let's go to our fuzz.py. We're going to need to import this. Let's go back here. Did they have it imported? Okay, they don't have it, they don't show the import there, but what we need to do is we can say from pwnlib dot format string, and we want to import format string payload, format string split, although I'm not too sure if we'll need all of those, but let's import them. Format string split, there we go. Okay, so we've got those imported, and then we want that function as well, the send payload. I'm just going to take a copy of that for now. Let's take a copy of that and we'll put it up here with the start function. And it's going to take in the payload. We're going to have this log info. I'm going to take that out. We're going to send the line payload, but then we know that it's going to bring back this hello. So let's just have here, we'll change this to IO, all these to IO. We're going to receive until we get the hello, and then we're going to send back the receive line after that. So it's just the same stuff that we're doing here. It's just rather than fuzzing this in a loop, they're going to do it for us, but they just need to know what's going to be sent and what's going to be returned here and what the format is. So with that in place, let's go and create our format string. We can go back to the example that they have here. Let's just grab a copy of some of this so we can see what we're working with, and we'll just leave that as it is. It's send payload. It's gonna do this for us and try to identify what the offset is. In fact, let us now, once this occurs, we can then say info, and we'll say format string offset, and then format string dot, and we can see we've got different parameters here. We can actually do find offset there as well. We can leak stack as well. I'm going to just do, let's actually have a quick look at that leak stack. Leak stack, offset, and prefix. Okay, does it? Alright, doesn't have any documentation there, does it? Okay, well, we're just going to print out the offset for now, so just set that to offset, and it's going to be essentially doing what we did here, where we, or well, not here, where we sent these A's and we tried to work out how much we need to write before we can actually get our values onto the stack so that we can then reference them. So whenever we were going to do the address, so we can put in an address here, for example, we could put in \x dead beef. I'm not going to do it all, but in little endian, and then we'll actually see that value on the stack. Let's take this out anyway. Let's comment out our writes and stuff for now, and let's just simply try and find out the offset with this and see what happens. So we do Python fuzz, we get the offset is 10. We didn't get too much information there. Let's put this on debug and see what's actually going on. And whenever we run it again, we'll see each instance what it sends. We can see there it's sending 21 bytes, and we can see then we have like some of our cyclic pattern, and then we have the start, and then it's actually giving, we've actually got a stack address there, and so each time it's leaking the address. It gets down to our 10th element, and then at this point, this is the first instance where it's actually found this cyclic pattern has been leaked from the stack. So it knows at this point, okay, the value that has been entered here has actually finally been detected on the stack, so therefore we need to write our values at an offset of 10 if we want to be able to reference them. So now things are starting to come together. We've got our writes here, we've got some examples of the writes we can do, and we know which values essentially we want to write. One of them is going to be the winner value. We want to overwrite this with a 0. This is going to be easy enough because we can just get this address 404078. So let's go back here. I'm going to say 0x404078. Was it 78? I've forgotten already. Yep, 78, and we want to overwrite it with a 0. So it's no problem, we can just do that, and we'll say here we're writing 0 at winner. The issue here is going to be our overwriting the random value, because the random value is not sitting somewhere in memory here for us to overwrite. We don't know the address of it. It's going to be added onto the stack, and we can leak the stack and find the offset. We know that we can leak the stack because we've seen the examples of that occurring. So let's actually, what I probably should have done is create a new file here. I'm going to create Codium, and we'll call one exploit.py. I'm going to put our write stuff in there and take out that fuzzing loop, and then we'll go back here and we'll just leave this to be the actual fuzzing loop. I'm going to go and undo basically all the format stuff that we've put in there. And get back our fuzzing loop. I'm going to go through and we're going to have a look. Let's print out the pointer values here. And we want to loop through and print out the pointer values, but we also want to be able to compare that to where the random value is on the stack. So let's clear this. Let's open up. I'm going to open up Radar with leak test, and then I'm going to do AA to analyze the functions, AFL to print these out. We'll do SMain to select it, and then we can do PDF and then have a look at the code. I could have also just grabbed this from inside Geardra or somewhere else, but it's all good. And here we want to try and find somewhere we want to actually set a breakpoint. So where's the comparison happening? We have the comparison happening right here. So let's grab this address, and we'll go and we can just place this into the breakpoint section here. It already had the 0, so we'll say B and then star, and we want to break at this address. And now we can just pass in GDB, and it should break for us. So let's go. Let me clear that. Oh, let me clear this. Let's do Python exploit GDB, and it's going to run. You'll see there. Oh, not the exploit. Let's do Python fuzz GDB, and we'll see that it's stopped after it's printed the A's. We've got this breakpoint right here. Oh my god. We've got this breakpoint right here. I'm going to hit enter, so it just stops at our breakpoint, and you can see that the next line that's going to be executed is this. It's going to multiply. It's going to multiply the 0, the leak code, with the value that's in the EAX. So let's go to our code here. We have this code. It's going to, let's go over to it. So we have 13C, which is our random variable, is being placed in the EAX, and then we have leak code is being multiplied with the value in the EAX, the random value, and it's being stored in the EDX, and then the EDX is going to be compared to the winner, which is going to be loaded into the EAX. So right now the EAX should contain our random value. Let's go and see if it does. Here we've got 8806, so that looks good. And whereabouts is it on the stack? Here it is, 8806. So this is a stack address. So if I take a copy of this, and we know this is our target, let's go. I'm going to go to ASCII to hex. This is our target, and let's go back here. I'm going to delete the breakpoints. I'm going to hit continue and just let that run through. And now we have some addresses that we can use to calculate this from. Now, whenever I was solving this, I tried using these earlier addresses, and I managed to get everything working locally, but had some problems remotely, and I'm not too sure why. So I ended up using this value here, the 39, which is just the third value, which is clearly a stack address. So that's fine. We take the 39th element, and let's go to ASCII to hex as well. We could actually just I'm gonna do Python -c, and we'll print. Let's put those 0x's back on there. We just want to find out what the difference is between these. So we paste that in, we get -287. So there's a 287 difference in decimal. So that's our offset. So let's bear that in mind. Let's go here and actually say we'll take from our fuzzing script. Actually, let's grab this code right here, and instead of passing in I, we're going to give it 39. Let's just try that. Let me try and print that out. Print result. We'll comment out this right for now, and run that. We'll run Python exploit without the GDB, and we get back 4014BD. Let's go back to our. So that was actually the 40th element because it's beginning at 0. So let's change this 38 We run that again, and this time we get this stack address, and presumably then if we calculate the offset, in fact, let's, as we've done in previous examples, we can, I'm just going to grab the code here to leak the address, to format the leaked address. So we grab the result. In fact, we'll say, instead of result, we'll say leaked address is equal to, I'm going to paste it in the whole thing there. Leaked address is equal to, and it's basically going to read the lines in as a string. It's going to strip anything from it, and then it's going to convert it into hex. So there we've got our leaked address, and now in fact we'll format this a little bit differently. We'll say info leaked address is equal to 0x %x, and then we can pass in our leaked address. Let's just test that out quickly. And we get a leaked address there. It looks good. What we also need to do is make sure we update it. So we're actually going to say the stack, or we'll say the random num address is equal to leaked address minus 287, and then let's also just print that out as well. And then we could pass this in. In fact, I'm going to take out this format string stuff because I want to run through these breakpoints, and I don't want to have to go through each of those. I don't want to have to keep hitting continue for each of those 10 breakpoints or whatever it's going to go through. So we'll do this Python exploit. We'll do GDB. Oh, does GDB have the? No, GDB doesn't have the breakpoint. Let's go and throw that in there. Take this breakpoint, put that in there, and let's try that again. We run it. Oh, it actually closed as well. Okay. Just to try and keep this open, I'm going to go back, and after this occurs, we'll do IO interactive. Let's run that again. Okay, we hit our breakpoint. We can see here that the random number address is right there. So let's go to our breakpoint here, and let's see. We know that it's in the RAX. This is the random value. It was loaded from devu random, and the address of that is ending with CE48. And if we look down at our code here, we can see indeed that we have CE48. We could also go and try to print that out, and oh, that's interesting. I wasn't expecting that. Okay, print the RAX. Well, the RAX we know is at that location anyway. We can see it there. So that's all matching up. Let's close that down. Now we know we have the address of the RAX, of the random variable in the RAX, which is going to be in the RAX for that comparison. So now we can actually test this out and see if the write works. Let's have a look. So I'm going to uncomment this code so it can identify the offset and stuff, okay, and so it actually has a format string object. And in here we're going to place, in here we're going to place 0 because that's what we want to write, but in here we're going to place the address of the random number. So we'll leave this breakpoint at the same place. So this is gonna let's just highlight this and see what it says. So it's going to write at this address that we provide, it's going to write this data that we provide. That's the only two variables it takes in. And then this execute writes is going to make a payload and send it to the vulnerable process. So it's going to execute both of these writes that we've prepared for it. One of which is pointing to the winner, which is Cafe Babe. One of which is pointing to the random number. So we're aiming here to ensure that the random number and the winner both equal 0. So anything times 0 equals 0, which means this condition will hold true. We also need a flag.txt, so you can see here that if this is all successful, it's going to open flag.txt and it's going to print that out. So let's actually create flag.txt, and we'll just put in here flag fake flag.txt, just so that's there for us to try and read it when the time comes. And with that in, let's run this again. I'm gonna put this on to, yeah, it's already on debug mode. Okay, we're gonna run it with GDB on and just verify exactly what's happening. So it runs. We need to go through these breakpoints here. We have you can see at each breakpoint it's fuzzing to find out when it gets this right. So it's finally found the cyclic pattern in the stack, and it knows that the offset is 10. And now it's going to send this 38. It's going to get the pointer of the 38th element on the stack. So let's allow it to do that as well. And then it's going to send our payload. So if we have a look at the RAX, the RAX currently contains F3FD, which is the random value. And we're about to have this multiplication with the RAX. Let's go to our next instruction. We hit next, and okay, we have the move there. Let's hit next again. Now we have the compare EDX and EAX. And these aren't empty. Let's see what's going on here. No, okay. Sorry you aren't late enough, come back. So that didn't actually work for us. Oh, but then we get our... We did get our flag there in the end. Okay. Let me try and run through that again. We run GDB. We go through our breakpoints to get through the fuzzing. We finally get to the end of that, and the RAX contains the value. Let's move this over. We can see a little bit more. Yeah, so the RAX contains the value here. Let's continue again so we can see the stack value here. So this is the random number address, and right here random number. Yep, that's the exact same address. So if we print that out, we see in there we have the 198C right now. Let's go next instruction. I'm going to hit continue, and then I'm going to check that again. Okay, so now that's been overwritten. So we needed to wait for that printf to come back. So it's come back with the printf, and that's actually executed that. And now you can see that the RAX, it's about to do this comparison. It's about to compare. It's about to multiply whatever's in the EAX here, which is 0, with whatever's in the EDX, which where's the EDX? 0, and oh, sorry, it's going to multiply the value in the EAX 0 with LeetCode, and it's going to compare it then with the value which is in the EDX down here. So let's move down. We go next. It's placed LeetCode times EAX in the EDX, so the EDX now equals 0 because anything times 0 equals 0. And now it's doing this move where it's going to move the value from winner. So let's actually quickly grab this and say what's there. We'll see winner, and actually winner has 0 in it, so winner should have Cafe Babe, but that's already been overwritten. So now if we go continue again, get to this compare. Oh, okay, I just skipped past I meant to hit next, but we get the idea. Alright, so that's worked for us. It's printed out the flag in that case. So if we run that again, let's run it without GDB, and we'll see, come right in, fake flag. We could turn off debug as well if we wanted to. Put this on info. Just make it a little bit cleaner. Oh, and then we get everything except we don't get the fake flag. So the issue there is we need to actually do a read here as well. So we'll say io.receive until come right in, which you see right here, come right in. We're going to take everything up until that space, and then whatever we receive after that is going to be our flag. So we'll say flag equals io.receive, and then we can print that out as a success message. Let's do that again, and let's spell everything correctly if we can. And we get our fake flag as expected. So we can try this against the remote server as well. Before we do that actually, let's just have a look and see what's going on. And we'll see what's going on behind the scenes, because previously whenever I was trying to solve this, I was trying to solve this manually without this format string function, and I wasn't able to. I solved it with this, and now I want to try and find out what's it actually sending. Let's run this, send exploit, and we can actually see here then, so it's sending %12 $LLN, %13 $LLNAA, and then we have our addresses as well. So our addresses here, where we have 404078, we can see, let me close this, we can see in little endian format here we have 404078, and again our leaked address, I can't see it right there, our leaked address right here, we have 2887483B, and you're seeing that go in the reverse order there. So there are addresses at the end. So let me move this over here, and let's try and do our usual payload without doing this format string stuff. I'm going to take this out. I'm going to take this out, and right here we'll try and just put this together as a payload. We'll say payload equals flat. As always, we're going to flatten it based on the context that we have defined up here, and we're going to pass in an array of elements. The first is going to be this %12 $LLN. There's one parameter I'm going to put in, and then we're going to put in our %13 $LLNAA. So it looks like this is actually just padding the AA. I would say that that is padding from the cyclic pattern, and then followed by our addresses. So our addresses, we can, do we need to pack here? Let me pack 0x404078, which is our winner address, and then we can pack the random number address. I'm just doing that based on this because we see our, first we have our winner address and then we have our random number address. So presumably, since I've formatted this payload exactly as they have here, if we run this again, we get invalid syntax because we've forgotten a comma. But now if we run it again, we, oops, don't get a flag. Okay. Oh, we're not sending our payload. That would help. So let's do io.sendLine payload. Let's try it one last time, and there we go. We get our fake flag. So all that's left for us to do now is run this against the remote server. Let's change this back to info. Let's go to hack the box and start an instance. And whenever I mentioned earlier that I was using different stack values, they all worked for me locally. It was just that this was the only one that worked for me remotely. Maybe I wasn't calculating something correctly, but it seems strange to me that it actually worked locally and not all remotely. Surely if I have the offsets right to work locally, then they'll work remotely as well. I don't know. So we run this. We just put in remote in capital letters. We remove this colon between the server and the port, and if we run that, we get back our flag. Awesome. So we know it's all working. We can go in, if we wanted to, we could just make sure it's working using the pwnTools method, which you'd like to hope it is, because that's what we based our payload off. and we can run that again, and we get back our flag as well. So what I'm going to do, I'm going to put a couple of different scripts online. I'll put a auto format script which uses this auto format function. I'll put a leak test script which is going to do the same thing, but we're going to use this payload. And I'll put up the fuzzing script as well, just to, if this might come in handy for any future CTFs, or if you just want to try and experiment with this a little bit more. I apologize if this hasn't been the kind of quality that maybe some of the other Pwn videos have been. It's just I found this a lot more difficult to solve than most of the buffer overflow challenges. Hopefully they'll be a little bit easier in future, but it's still kind of a little bit, I still find the whole format string vulnerability issue a little bit confusing. I'm still not 100% sure about why it's formatted the payload exactly as it has. It didn't match up with the things that I was trying manually. So check out some of the links anyway in the description. There's a lot of really good write-ups which, if you can understand them, I'm sure will really help you in challenges like this. I struggled with some of them. Some of them were a lot more complex. Although they're looking at the same vulnerability, they were a lot more complex challenges. And anyway, yeah, I'm rambling now. It's been a long video. So I hope you've enjoyed it anyway. If you have any questions, comments, you can leave them down below. Thanks.